Okay, new section time. So we've been talking about tangent line slope, so like a really geometric, notion of what's going on, looking for a line that runs kind of in the same direction as a function's graph. And then we ended up arriving at this calculus construct that we call the derivative that ends up linking these two things together. So it ends up, representing this tangent line slope thing. So on the one hand, we have the derivative. Like I said, students often think of the derivative as a very formulaic thing because it ends up arising like as a function that we get from another function. And then we saw that it's got this geometric interpretation. It's the slope of a tangent line at a given point, and we can use that to say, stuff about a particular function. In the next chapter, not to foreshadow too much, we're going to end up doing a lot of that when, in an application sense. But as it turns out, these two guys are basically, one and the same thing. And I mentioned, Gottfried Wilhelm Leibniz, one of the two men who developed calculus in the 1600s. He was kind of looking at things from a geometric point of view. And I'd also said sort of the more famous guy who ended up getting connected with the development of calculus is Sir Isaac Newton, and he was coming at things from a different direction. It's not that he wasn't doing geometry. There's geometry all over the book where he published his results. Not that I'm suggesting you look at it; it's really technical. But we often think of Newton as a physicist, right? He was working on physics problems, celestial motion, gravity, that kind of stuff. And as it turns out, he sort of ended up at the same place because when you look at stuff like that in sort of an applied, scientific, some other, technical context, he was considering rates of change of various things. We'll stick to kind of as you said, generally focused on sort of like physics type examples. It's okay if you haven't taken a physics class, it's okay. We'll walk through it. But rates of change. So you can talk about rates of growth, rates of decay, that sort of thing. It's not just a physics thing. You talk about reaction rates and stuff in a chemistry class. Economists are worried about rates of change of things like prices of goods and things of that nature. So it ends up coming all over the place. So as it turns out, if you were to plot the points of some data set that you go gather in a laboratory, to represent a function, and then connect those points up with with a curve of some sort, your rate of change, one rate of change we'll talk about in particular is the velocity of an object that's in motion. It turns out that velocity and that tangent line are actually kind of the same thing. And by kinda, I mean they are the same thing. So it turns out we end up with all three of these quantities, sort of like the purely mathematical object, the geometric, visual object, and then the scientific applications object are all in fact one and the same thing. So it's really I'll often refer to this as the circle of calculus. These three things are really just all the same object viewed through different lenses, so to speak. So we said, I call this the circle of calculus. It's not in our textbook. It's not in any textbook to the best of my knowledge. I'm the only person who's ever put these things together like this. So anyway. So I mentioned I want to take a look at this in the context of sort of one of the classical physics examples, dealing with an object in motion and trying to relate its position and its velocity and things of that nature. So my calculus instructor as an undergraduate often referred to calculus as finding a way to describe the relationship between your car's odometer, its speedometer, and its accelerator. We'll get to what that all means in just a second. But I did want to, put up the circle of calculus here just as a note. So try to remember these three things are really all different sides of the same coin. Doesn't make sense because there's three of them, but you get the idea. All right, let me clear this off, and then we'll start taking a look at an example. All right, so I want to take a look at this notion of velocity and how it ends up intersecting this tangent line derivative stuff we've already talked about. So as an example, I've posted a worksheet in Moodle that kind of goes through all of the bits that I've got here, but you'll be able to follow along, I think, even if you don't have a printout of it handy. By all means, go grab it if you'd like. But so the idea here is kind of the classic object in free fall kind of thing. So we're standing 200 feet over a cliff and we let something go, whatever it is. A vague object is released from 200 feet up in the air. Those of you who are fans of the metric system, I apologize. Calculus textbooks have this thing where we tend to use British units here in the U.S. I apologize in advance. I'm kind of a fan of the metric system myself, but you play the hand you're dealt, right? Anyway, so we're 200 feet up in the air. We drop an object. Now, I'm not going to belabor the point as to where this is going to end up coming from. By the time the course is done, we'll have seen where this ends up arising. But if we do sort of the usual, let's assume air resistance isn't having a massive impact on this thing. It's super duper aerodynamic. So then our position as a function of time is going to look like this guy here, negative 16t squared plus 200. This is how high above the bottom of the valley or canyon or whatever we've dropped this thing over is t seconds after we release it. So S of t equals negative 16t squared plus 200. Now, so I'm going to use the term velocity here. A lot of people will use the word speed in the same context. From a scientific standpoint, they're not really the same. Velocity technically takes direction into account, so you can have a negative velocity if something is moving, in the downward direction. That's kind of our default assumption here. All right, so if we look over a given interval of time, so we look at this thing, say 1 second, after it's been released, and then we chart its position again somehow using fancy cameras or something like that 1 second later. So we know how far it had fallen after 1 second and after 2 seconds, and we want to know how fast was it moving. The usual answer we would give is what we call an average velocity. So I'll call it AVE for average. If you wanted to use some other notation, that's fine. So what we're going to do is, you might remember, that speed is like distance over time or something like that you've seen like in a physical science class or something along those lines. So we're going to have here, we figure out how far the thing traveled. So where it is at the end of our time frame minus wherever it started over the amount of time that's passed. 2 minus 1. If you just put a 1 right there, that's totally understandable. So now we can plug in, t equals 2 into this guy right here, plug in t equals 1, get some numbers, and see what ends up happening. When I plug t equals 2 into this, I should get negative 16 times 2 squared is 4, so negative 64 plus 200, so I'd have 136. When I plug in 1, I get negative 16 plus 200, so that should be over 184. And then we just have a 1 underneath. So if I'm doing my arithmetic right, this is going to end up giving me, I say approximately, that's actually like an exact equality, right? So feel free to replace the squiggly equals with So anyway, so our units, or a velocity, we could mention, for now we're measuring them in feet per second, because that's what the time units are in this instance. I know you'll often talk about things like miles per hour, kilometers per hour, but we're dealing with a much smaller scale here. So negative 48 feet per second. Again, the negative in this instance indicates that our object is traveling downward. If we'd thrown it up in the air initially, then a positive velocity would mean that it's flying upward. One-dimensional motion. Don't worry about arcing or anything like that. All right. Now, that's not a terribly specific, velocity, in the grand scheme of things. We can tighten this up. So, what if we wanted to look over a smaller time interval? Like, say, for instance, from a 1 to 1.5 seconds. So we cut the interval of time we're looking at in half. Same idea. S of 1.5 minus S of 1 over 1.5 minus 1 of... All right, so I actually needed to stop and check this one to make sure I did it right. When I plug 1.5 in here and fill out the arithmetic, I got 164. Plugging in 1, nothing's changed, minus 184 divided by 0.5 when I take the difference of that stuff. I won't put the squiggly equals this time because, again, it's, so negative 20 divided by 0.5, so we have negative 40 feet per second in this instance. All right. So on the worksheet, it goes even a little bit deeper. What if I cut this down to 1.1? You might notice at this point, this is feeling awfully familiar because it's the same kind of thing that we just did with the tangent line thing. This looks, essentially, this average velocity looks like a secant line slope calculation. So yeah, we keep tightening our time interval up lower and lower and lower and lower and lower, and lo and behold, we can talk about what we call the instantaneous velocity of an object, rather than an average velocity. How fast is our object moving at a specific instant in time? So, and it turns out, dropping the average, we can say v of t, at a particular t value, is in fact a limit that ends up looking really similar. I could go rephrasing it, but we have s of t plus h. So again, that's some little fudge factor where we're bumped off the target point. Minus s of t all over h, that time interval that we're interested in. We let that interval shrink down to 0. And you probably get the idea here. That's exactly what we were doing with our tangent line problem, where we ended up coming up with this thing we call the derivative. So our velocity function is, in point of fact, the derivative of the position function that we were handed in the first place. All right, so now that we've got this set up, this instantaneous velocity is the same thing as derivative, is the same thing as tangent line slope. In our next video, we'll dig in and actually get a formula for our generic object's velocity, and then answer some questions, and then look at another example. So, yep, that's what's coming up.